Okay, here's that overview of different types of functions, right? So, of course, the new thing we want to focus on are these over here, but let's actually do a little bit of comparison of things, okay? So, I think the two big questions I'd like to try to address are how do you visualize? Okay, and then the other big question I'd like to talk about is what is its model? So I think both of the questions are important for this right here, for vector fields, our new type of creature. How do you visualize them? And what do they model? Or why do we care about these things, right? So um, we'll answer both of these questions in turn, but let's start with how do you visualize? And in fact, what I want to do is go back and review how do we visualize all these other ones. Uh, Now, each of these four categories of things over here are really, I guess, in the end, different kinds of creatures, and they require different kind of visualization. So let's answer this how do you visualize question by, again, splitting this up here, type of output, and then number of input variables. So, one input variable, or maybe you have two or three input variables, and then is the output a scalar versus is the output a vector. So, how have we visualized? Well, uh, back here, this is the easiest one. You graph. You graph y equals f of x. Yeah? So, what could this model, for instance? Oh, I guess we're going to answer this question along the way. Like, it could be a picture of position versus time. Of course, there's lots of other options of, you know, time doesn't have to be your x-axis, position doesn't have to be your y-axis, but it's just a possibility. So what about one input variable and the output is a vector? Really what you do is for that vector function, like over here, you just draw the associated parametric curve. That's how we've been really visualizing. Draw a parametric curve. Okay, remember this models, what is this model? It models the motion of a particle. I just mean that to mean a tiny, tiny little point that can move around. So that's why I've been going with like a bug, okay, in 2D or 3D space. What about over here? Two or three input variables, and then the output is a scalar. So this type of thing over here, well, we'll just graph. Yeah, so this has been a graph of, let's just go with the two input variable story, right? Graph like z equals f of x comma y, for instance. Or we've looked at level sets. So level sets like, f of x comma y equals a fixed value k, because that's going to be a two-dimensional picture, or f of x comma y comma z is equal to a fixed number k. That's going to be a three-dimensional picture. It's the only thing you can really do if there are three input variables. The graph, unfortunately, would be four-dimensional. Now, what goes over here? So how do we visualize and what does it model? Well, let's take the example of capital F of x comma y equals angle bracket negative y comma x, the one we had been already dealing with. So how do we draw? What's a way to draw this? Now this is going to be a little cumbersome, but it's in a sense the best we have. So what we'll do is at the point 1 comma 2, at that point, draw in the vector. Draw the vector. We already computed what the output was, yeah? The vector negative 2 comma 1. Just draw that vector negative 2 comma 1 located at the point 1 comma 2. At the point 1 comma 3, draw the vector bracket negative 3 comma 1. Okay, so let's go ahead and draw a very, very quick picture of these things. Right, so like that, yeah, x-axis, y-axis, 1, 2, 3, 4. Something like 1, 2, 3. Let's just go with that. So then at the point 1 comma 2, so at this point, we need to draw in the vector negative 2 comma 1. So from here, if it just starts at this point, 2 units over to the left, so like right here, negative 1, and then 1 up. So this vector, okay? And so cool, at the point 1, 2 here, we drew in the vector negative 2 comma 1, so that arrow has been drawn in. Okay, And then at the point 1 comma 3, draw in the vector -3 comma 1. So that should end up, that's where the arrow should end up pointing. Yeah. So yeah, so from the point 1 comma 3, we draw the vector -3 comma 1. So at every single point here, yeah, so at this point, and at this point, and at that point, and at this point, and at this point, you just draw in the appropriate vector. And you don't want to draw in at every single point because, first of all, who has the time? And if you draw in too much, we can't really see what's going on. So this is time consuming to draw, for sure. But just remember when you were first drawing y equals x squared, that was also consuming to draw in a bunch of individual points from an xy table. But you know, that's what you have. Just in this case, we don't want to draw in too many arrows because it will be visually distracting. Let's go ahead and look at an app that's going to do this for us. All right, this is not an app that I have designed. Somebody else, Juan Carlos Ponce Campuzano, has designed this, and I just found this online on GeoGebra, so I'll post a link to it. By default, so there are some instructions so you can change which vector field is here, but by default, and I have to apologize that there's parentheses here and there. I guess the person who designed this might be teaching calculus using a different textbook that has slightly different notation. For us, it'd be an angle bracket there and there. But the vector field has first component sine of x plus y and second component cosine of x minus y, at least by default. Let's go ahead and throw in the one that we had. I believe, wasn't it -y for the first component and positive x for the next component. So here's what ours looks like. And what we had done just a moment ago was at 1 comma 2, was it? I'm going to have to zoom out just a little bit and maybe decrease the density. Too many arrows here. So yeah, I guess, oh, this is really neat. So too many arrows and it's too hard to tell really what's going on for sure. So we went to 1 comma 2 and drew in an arrow here. And due to the density not being enough, we just didn't see that. I guess we're just still missing it. But there's that arrow. And then at 1 comma 3, it looks like essentially this arrow right here, right? So at each point, you should draw in an arrow. But if you draw in too many arrows, it's too confusing what's going on, especially like with what was here by default. If I reload it, I wonder if the default's going to reappear. Let's just go ahead and try this. Yeah, so it looked like the default one that the designer put in is, so some very different looking vector field. And if you change the density, there comes a point where it's too hard to really tell what's going on because there's too many arrows. So let's kind of now there's just the right number of arrows where you can kind of really actually see what's going on. Too much information is just overwhelming here. Okay, so we have some apps that are available that's going to do some of the drawing for us, but I think it was helpful to see just by hand what is it that the apps are doing. They're just picking a couple locations in the plane and at each point just drawing an arrow. But then the next question is, what is this model? We should talk about that, right? So what do vector fields model? Now, on some level, the answers, and it will be plural. We're going to provide 1, 2, 3, 4, 5 answers to this question in a moment. The answers to this question, in part, are for the purpose of why do we care? But if you look at any of the 5 answers that we're about to go through, and you don't care about the specific application here, that doesn't mean to just ignore this. The thing is, because vector fields are new, at least having some examples of what vector fields can model can also help clarify what vector fields are in the first place. So please don't just look at an example here and go, oh, well, I don't care about that example. Think about this more as like this is a new concept and we should try to understand what's going on. So first, as a first example, vector fields can model. So first of all, the most plain answer is just to say, well, when can you have a situation where at each point in two-dimensional space you can get a 2D vector, or at each point in 3D space you get a 3D vector? That's any type of situation of that kind is what vector fields model, but let's give real specific examples. How about currents? So at each point, at each point in a body of water, you there's a vector. Remember that a vector is really just a direction and a magnitude. So at each point in a body of water, there is a vector attached. And that vector, if it's really a direction and a magnitude showing that kind of movement, then this is really something that would be called a velocity field. So it's just a fancy name. You don't need to know this name. I'm just saying that a velocity field is a special kind of vector field, and all it is at each point, you're really seeing the movement. If you could see this visualization with the arrows here. So I actually was at a restaurant in Onalaska with some colleagues, and I did not have my phone with me. This was years ago, but I asked my colleague Dr. Das to take a picture, or not a picture, rather a video. And I think you can see in the video that we're about to show the currents. You can really visualize what's going on. So let me just load that video up. Just give me a second. Okay, so this is slow motion of just a really cool tank of water. They just put in some lights for color. Don't worry about the color, but I think it doesn't even matter that the colors are changing, but you'll notice, let me just reload the thing now. You'll notice that even if they just stuck with one color, you can really, due to the color and seeing the light or seeing the water do its thing to absorb the light, I guess, you can really see how the water is moving. They just probably had a little, some jet streams installed into this thing. And while the movement of all this in time is actually adding a layer of complication that I don't want, even based on the movement you see, if I just pause the video right at this moment, you knew just because I was playing it earlier that right here, say, the water was moving mostly up, slightly to the left. And so at this location, you'd attach a vector that's like mostly like this. Let me go back and maybe at that location, you draw a vector that looked like that, right? So this is an example. Let's have another. So that's example one. Let's look at example two here. How about currents, again, at each point in 3D space? And what would this be a current of? Well, if you're in 3D space, probably wind. So at each location, so go and just hold your finger up in the air somewhere, and maybe you're indoors right now while watching this video. So maybe there's no wind. But if you're outside, even on a not so windy day, maybe there's a little bit of wind at the point where your finger, at the tip of your finger. And then 1 unit higher, 1 meter higher than where your finger is, that's a different point in 3D space. There'd be probably a slightly different amount of wind, and it might be pointing a slightly different direction. Now, to oversimplify things a little bit, let's just think about just the wind right at ground level or something, or where instruments can detect the wind. And I found this really neat website, or rather 2 websites online that happen to visualize wind around the world based on, I guess, weather data. All right, so here is a website called WindMap, and I believe what they're doing is showing current wind at, you can kind of just see, and again, things are moving, so this is cartoon-ish, and it's because of the movement, and of course things are changing at each second. The wind is not, even if the wind is going perfectly north right around Dallas here, that's going to change, right? A second later, the wind is probably still going to go north, but maybe not perfectly north anymore, or something like that. So the fact that this is evolving over time is adding a layer of complication that I don't want to. But if I could pause this is not a video, it's a website app thing. If I could pause it, because you were seeing the movement a moment ago, you would be able to go, oh yeah, I should attach an upward arrow here versus, somewhere over here in Montana, I should attach a northeast arrow. Is there any place where the wind is going south? Yeah, like right over here somewhere. Yeah, it looks like the wind is traveling in towards Phoenix, up from the north down southward, slightly westward. And you can, I think there's a way to zoom in. Yeah, so yeah, it's kind of a neat thing to take a look at here. And actually, I forgot that you can do this. So at a specific location, so think of like the 39 degrees, 94 degrees, so north and west. That's the point of input, and you're seeing the speed of the wind is 6.8, so that'd be the magnitude of the vector there. Here's another visualization. It's maybe, of course, the Earth is round, but if you I just zoom in somewhere, let's go. How about right here, right in Middle East? Is it going to show? Yeah, there we go. So you'll see wind data, and you're seeing that somewhere here. I guess this is Iran, roughly, right? That the wind is mostly south, somewhat going to the east, right? So what's a little kind of funky about this is while the Earth is round, and so there should be some 3D thing going on. If we just pretend that the world is flat, then this would be just pretend the world is flat here, and you kind of could sort of pretend that it was. Then in this area, each location, each XY coordinate gives you a 2D vector of wind. Okay, let's look at a couple other examples. So you could have, as a third example, what about force? So you might have a situation where at each point in 2D space or at each point in 3D space, there's a different force, and force is a vector, so there's a different force at each location, and this would be called a force field. And a force is really just informally, it's just a push. You might have, as another example, well, since gravity is a type of force, this is just really a sub-example. Gravity as a force, this is what's called a gravity field or a gravitational field. So the effect of gravity at each point in 2D space or 3D space creates a vector field, which is called a gravitational field. And then as another example of a vector field, electric force. So you could say that that electricity, a source of electricity somewhere, at each point ends up placing a certain amount of electricity. I'm speaking totally outside of my wheelhouse here, but creates a certain amount of force, again, I think, at each location in 2D space or 3D space. And so this creates what's called an electric field. Again, just at each point in 2D space or 3D space, if there's a vector that you can attach as the output, then that's a vector field.